Thanks. Okay, so today I will talk about parallel graph connectivity in log diameter runs. This is a joint work with Alex Andoni, Zhao Song, Cliff Stan, and Zheng Yuan. So recently, several parallel systems such as MapReduce, Hadoop, and Spark have become very successful in practice. And this success has sparked a renewed interest in algorithm ideas for these parallel systems. So one of a very important theoretic direction is to design a good model for these parallel systems and to relate them to the classic models such as PRAM model. One of the model is called massively parallel computation model, or just the MPC model. I think this is a very good model in the sense it balances the theoretic, accurate modeling with theoretic elegance. So today I will talk about how to design a graph connectivity algorithm in this model. Before I talk about our algorithm, let me first introduce the model. So in this model, you have input data with size capital N, and in the system, you have P machines, and each machine has local memory size S. So before the computation, the input data is distributed arbitrarily in the machines. And each machine just holds a part of data with size at most S. In our work, we care about the most restrictive case. So the number of machines times the local memory size is just linear in the input size. It means that the total space available in the whole system is just linear in the input size. Furthermore, the local memory size is sublinear in the input size. So it means that there's no machine can hold the entire data. So to compute the final results, they need to communicate and to coordinate to each other. In this model, the computation processing runs. So at the beginning, each machine just holds a part of the input data in its local memory, and in a single round, each machine can do some local computation based on the data stored in its local memory. And at the end of this round, they can communicate to arbitrary machines. However, there's a restriction. So each machine in a single round can only send or receive the data with at most S. This is because each machine just has local memory size at most S, so it cannot send or receive more data. Otherwise, it cannot fit into the local memory. The data received by a machine at the end of this round will be stored in its local memory and will be used for the next round computation. At the end of the computation, the output will be stored in several machines. Our goal is to design an algorithm which minimizes the total number of rounds of communication and the computation. So why should we study graph problems in MPC model? Graphs, especially large graphs, are very natural benchmarks of parallel distributed models. For example, in our real life, there are many large graphs, such as social networks or transportation networks. They have billion or million or billion number of vertices and edges. So we need some large-scale computational system to handle the dataset. Furthermore, the dependencies between the vertices and the edges may be very complicated. So it always needs some novel and non-trivial algorithm ideas to handle these issues in the parallel models. And there is a long line of works that the graph problems in MPC model. For example, for graph connectivity, maximum matching, minimum spanning tree, vertex edge covers, or minimum cuts. And the graph connectivity problem is a very fundamental problem, so this is why we should study this problem. So what's the graph connectivity problem in MPC model? You have an n-vertex m-edge graph, and the input just the edges of this graph. So the input size is just the m, and this is also your total space you have in the system. So we want to output the connected components of this graph. So how to represent the connected components of this graph? We can use n pairs. So after the computations, these n pairs can distribute their own arbitrary machines, and each pair is just the vertex color pair. It means that each vertex is assigned a color. So for any two vertices v and v prime, they are in the same connected component if and only if they are assigned by the same color. There are several previous works that study this problem, so just remember the total space is just the m, which is the number of edges, and small n denotes the number of vertices. In the scenario when the local memory size is much larger than the number of vertices, let's say n to the 1 plus some small constant, then we can do it in constant number of runs by using some so-called filtering technique. And later on, when the local memory size is just linear in the number of vertices, we can still do it in constant number of runs. Actually, we can just simulate a congested click algorithm in the MPC model. However, in a scenario when the local memory size is much smaller than the number of vertices, then the only algorithm we know is just log n number of runs. Actually, there's a log n number of runs algorithm in PRM model known for more than 35 years. And we can simulate any PRM algorithm in MPC model. So it directly gives a log n number of runs MPC algorithm. And there's another simple randomized algorithm which also takes log n number of runs. However, all the algorithms known in this scenario will take log n number of runs. So a natural question is that, can we design a MPC graph connectivity algorithm which is faster than log n number of runs, and the local memory size is much smaller than the number of vertices? Because as I mentioned before, if your local memory size is much larger or just linear in the number of vertices, then we can do it in constant number of runs. So the only interesting case is when the local memory size is small. It's much smaller than the number of vertices. There's a log n lower bound for tuple-based MPC model. It's just a variant of MPC model, and there's more restriction on the messages you can send. And log n is also conjectured to be necessary in the worst case in MPC model. However, a super constant lower bound will imply a stronger circuit lower bound. So it should be very hard to prove a lower bound in the MPC model. There's some recent developments on this problem. So for the random graphs, one can show that we can use log n runs to find all the connected components. And there's another work shows that we can use log n number of runs to find all the connected components with good spectrum gap. Here we state our main results. So we give a faster, fully scalable algorithm for the connected problem. We just bypass the conjectured log n lower bound by parameterizing the round complexity as a function of the diameter d. Here, the diameter is the largest diameter of all of its connected components. Precisely, our algorithm takes log d times log n number of runs, where the base of the second log is just the m over n. M is the total space, or just the number of edges, and n is the number of vertices you have. And so if you are a dense graph, in this case, you have more total space. It's n to the 1 plus some small constants, then it's just a log diameter number of runs. We heard that parameterizing in diameter d is very standard in distributed computing literature. And there's a heuristic algorithm which is conjectured to obtain log diameter number of runs. However, we show a counterexample for their algorithm. Furthermore, our algorithm is fully scalable. Our algorithm works for any local memory size. And our algorithm works for general graphs. So we don't need to make any assumption on the input graph. For the special cases such as random graphs and graphs with a large spectrum gap, then we show a log n square number of runs, because in this case, the random graphs and the graphs with large spectrum gap, they have log n diameter. And so our algorithm is just slightly worse than the algorithm I mentioned before, but our algorithm works for general graphs. OK, so let's go to the technical part. Because of the time limit, I will omit the details of how to implement the algorithm in MPC model. I will just roughly give the high-level idea of our algorithm. So firstly, let me introduce a framework called leader construction. So you have an input graph G, and we just want to choose some leaders. So we randomly choose some vertices as leaders. For each non-leader vertex, if there's a leader neighbor of this vertex, then we just contract this non-leader vertex to its leader neighbor. And then we repeat this procedure until every connected component contracted to a single vertex. So a problem is how to choose leaders. In the original paper, they choose leader with probability 1/2. So in each round, they can choose a constant fraction of the vertices as leaders. And there's also a constant fraction of the vertices which are non-leader vertices. So for each non-leader vertex with at least a constant probability, it will have at least one leader neighbor. So each round, we can contract a constant fraction of the vertices. And actually, this is almost optimal for the path graphs. But if you choose probability 1/2, then you always need log n number of rounds, because each time there are always a constant fraction of the vertices will be leaders. So can we do better if the graph has a better structure? The answer is yes. So we consider a graph with n number of vertices. Each vertex has degree at least d. Here d is just the degree parameter, and it's just the threshold, and it can be any value, such as a constant or polylog or polynomial in n. Okay. So for this high degree graph, if we choose each vertex as a leader with a probability log n over d, then with high probability, good things will happen. So the first thing is that the number of leaders will just be n over d. Furthermore, every non-leader vertex will have at least one leader neighbor. So after we do the contraction, every non-leader vertices will be contracted. Because the number of leaders is just the n over d. So only a 1 over d fraction of the vertices will be survived after the contraction. And we show a very crucial thing. So if we can convert an arbitrary n-vertex graph to a high-degree graph, so high-degree graph means that you have a uniformly large degree d. And if we just use n times poly d total space, then we will have a log n number of iterations algorithm. So the problem remaining is how to convert an arbitrary input graph to a high-degree graph. So one of our main contribution is to design such procedure. So given an n-vertex graph G and the degree parameter D, we have a following MPC procedure as the following. It's called neighbor increment, and it takes the graph G and the parameter D as input. And we can output a graph G prime such that the graph G prime preserves the connectivity of the graph G. And each vertex in graph G prime has degree at least D. So it is a high degree graph. And this procedure takes log diameter number of rounds. And the total space needed for this procedure is just n times d squared. Notice that we only care about the total space for this procedure, and it can work for any local memory size. So how to implement this procedure? Actually, we propose a novel truncated broadcasting scheme. For each vertex with degree smaller than d, we do the following step. So if there is a neighbor u with degree larger than d, then we can just make the neighbors of u be the new neighbors of vertex v. Otherwise, if every neighbor of v has degree less than d, then we just do the broadcasting. So we make the neighbors of v be the new neighbors of v. And then we check if every vertex has degree at least d, then we're done. We just end the procedure. Otherwise, we repeat the above steps. Now let's briefly analyze this procedure. So if there's a vertex with degree smaller than d, and if there's a neighbor u with degree larger than d, then because we make the neighbors of u be the new neighbors of v, so there's an extra space d induced by this vertex v. And after this step, vertex v will always have degree at least d in the remaining number of rounds. Okay, in the second case, if all the neighbors of vertex v has degree smaller than d, then we do the broadcasting. In this case, the extra space induced by vertex v will be at most d squared. And after this step, after the ith round, if v is in this case, we will know all the neighbors within distance 2 to the I in the original graph after the ith round. And this implies that this procedure will be end in log diameter number of rounds. Okay, so we can build our whole algorithm. So you have an input graph G, and we initialize the graph G1 to be the input graph. If after the ith iteration, if every single vertex is a connected component, then we can just output all the connected components. Otherwise, we try to run the neighbor increment procedure. We first set the degree parameter di to be square root of total space over the number of your current vertices. And then we run neighbor increment procedure. It takes the current graph, gi, and the current parameter di as the input, and will output a graph gi prime. And this graph gi prime will preserve the connected components of this graph gi. And each vertex will have degree at least di. So graph gi prime is just a high degree graph. And this procedure will end in log diameter number of runs. Notice that this diameter is the diameter of the current graph gi. However, because the current graph gi is obtained by contracting the number of vertices of the original graph G, so this diameter is at most the diameter of the original graph. And the total space needed is just ni times di squared, because we set this di to be this value, so the total space needed is just the total space in the system. So we can run this procedure in our system. We have enough space. Then because gi prime has very high degree, then we can choose each vertex as a leader with probability about 1 over di. And as I mentioned before, each non-leader vertex will have at least one leader neighbor. So after the contraction, all the non-leader vertices will be contracted. And we let this gi plus 1 be the contracted graph. Then we repeat the previous procedure until every single connected component contracted to a single vertex. Then we can output all the connected components. So let's analyze the number of iterations. Because we set, so in the ith iteration, we set the parameter di be this quantity, and after the ith iteration, the number of vertices survived is just ni over di. So by a simple calculation, we can know that after the ith iteration, the number of vertices survived is just the number of vertices in the original graph over some quantity. And this quantity is double exponential in the number of iterations. This means that after log n number of iterations, our algorithm will stop. And because in each iteration, we need to run a neighbor increment procedure, and it will take log diameter number of runs. So the total number of runs is just log diameter times log n. Well, our main result is a log diameter number of runs connectivity algorithm in MPC model. Our techniques can be extended to related problems. For example, for the spanning forest, we can find the spanning forest in the same number of runs, and the byproduct of our spanning forest algorithm is a diameter estimator. Furthermore, we can apply our spanning forest algorithm and the connectivity algorithm to find the DFS sequence of a forest. And our algorithm can also be applied for exact or approximate minimum spanning forest and for the bottleneck spanning forest. Here's some open problems. So can we get a log diameter number of runs algorithm? Because in our algorithm, we have that log n factor. And is it possible to design a simple deterministic algorithm? That's all, thanks. Can you repeat your question?
There's a paper online. I haven't been able to verify.
Oh, I verified that. So the counterexample shown in our paper is also a counterexample for their algorithm. So I checked their proof. There's some trouble in their proof. But I'm not sure whether their algorithm is a log n number of runs algorithm. But it's definitely not a log diameter number of runs algorithm. Okay.
Does the complexity of your algorithm
Oh, so it's just 1 over. So for a single machine, you have input size to delta local memory. So we just hide the 1 over delta, that constant in our complexity.
Okay,
Yeah.
so if we imagine that delta isn't constant, but it's little of 1, algorithm works, but it's a little slower, yes?
Right, right,
Okay.
right. Yeah, so in the MPC model, we just assume that delta is a constant. But if it's not a constant, we just induce another 1 over delta, this complexity in our final complexity. Yeah. Yeah.
Is there a reason why you used the word simple in there, as opposed to just design a deterministic algorithm?
Okay, because I think our randomized algorithm is very simple. And so if you design a complicated deterministic algorithm, I'm not sure whether it's good enough in practice.